Morning, folks. We'll give it another minute or so before we get started. All right, I think the attendance list is pretty much converged, so why don't we go ahead and get started. For once, I don't think I have anything in the way of announcements or logistics to discuss. I think everybody knows that the regrades are due on Friday. I've gotten one of those submitted thus far. Hopefully lots of other people are busily working on it. I have office hours tomorrow as usual. If you have questions, you're welcome to drop by. Do you guys have any questions or concerns that you'd like to discuss before we dive into time-dependent perturbation theory? Okay, if not, then let's recap what we talked about previously, because the cornerstone of today's derivations is something we already worked out when we talked about time-independent perturbation theory. So the picture that I really want you to commit to your understanding is this picture. This is what perturbation theory looks like in general, whether you're talking about time-dependent or time-independent perturbation theory. This is the picture of what I would call the dressed propagator. The propagator means the time evolution operator. This tells you how the system starts off at some initial time and then evolves to some later time. This thick orange line is the dressed propagator because this is the full solution to the perturbed Hamiltonian, including the perturbation. And in perturbation theory, this is a power series in order by order, counting the number of interactions with that perturbation. So at zeroth order in perturbation, there is no perturbation. You just have the free or bare propagator, U0, which evolves you with the unperturbed Hamiltonian from t equals 0 to t. Plus, at first order in perturbation theory, you have exactly one interaction with the perturbation. That can happen at any time t prime between the initial state and the final state. So you have an integral over all possible times at which this perturbation could have been inserted. At second order, you have two perturbations, so you have two integrals over t prime and t double prime for the times when the two interactions could have been inserted, and so on and so forth. You have an entire power series in this thing. So this corresponds to this integral expression that we derived previously. This is the dressed propagator u of t. At zeroth order, it is the bare propagator u0 of t, plus the first correction coming from that integral over t prime from 0 to t, and then this operator expression corresponds exactly to this diagram. You have a bare propagator from t equals 0 to t prime, which is this guy. You have, in the case we were dealing with before, a time-independent perturbation that was inserted next. And then after that, you have free propagation, the bare propagator from t prime to your endpoint at t. And the critical statement is that nothing really changes about this picture when we go from time-independent perturbation theory to time-dependent perturbation theory. This picture of the perturbation series is a very powerful approach, which we derived by going to the interaction picture. And the only thing that's going to change is I'm going to insert a time dependence right here for the interacting Hamiltonian. So let's remind ourselves how this came about. So for the case now of a time-dependent perturbation, so I will write h of t is a time-independent h naught plus a time-dependent perturbation h1 of t. And for the purposes of our discussion today, I'm not going to try and write any coupling constant g for power counting purposes. I think that's just going to confuse things when we do examples with spin, which have their own Landé g factors. So the way in which we constructed this equation was we defined the interaction picture. Think of it like a moving frame that cancels out the time dependence of the bare Hamiltonian h naught, so you can clearly see the effect of the interaction or the perturbation h1. So we define the wave function at time t is the bare time evolution operator u naught, let's say to t from some initial condition t naught. And then after I remove that effect, this is what defines the interaction picture wave function psi I at time t. This is analogous to the case of paramagnetic resonance when we went to a rotating frame. And this was the wave function seen in that rotating frame. Now, when we derived this thing before, we were talking about time evolution from t equals 0 to some time t. For our purposes today, we'll leave the initial time arbitrary, starting at some t naught, because sometimes it's useful to start with an initial condition at t equals 0. Sometimes it's useful to start with an initial condition in the infinite past at t goes to minus infinity. So for now, we'll keep this arbitrary. So after we go to the interaction picture, and I guess, by the way, I should say, this bare time evolution operator is simple. This is e to the minus I over h bar, bare Hamiltonian h naught times t minus t naught. So when we do this, we plug this into the time-dependent Schrodinger equation, and as expected, the time-dependent Schrodinger equation in this moving frame in the interaction picture subtracts out the effect of the bare Hamiltonian h naught as intended. So we get something which is u naught dagger of t minus t naught h1 of t u naught of t minus t naught. So this looks like the Schrodinger equation in the moving frame. It's driven entirely by h1, but rotated from the lab frame, so to speak, to this moving frame. Once we had this, we converted it to an integral equation as the solution, quote unquote. So in the moving frame, the solution was psi I of t is the initial condition psi I of t naught minus I over h bar integral dt prime from t naught to t. And then we had this interaction picture Hamiltonian. So this whole thing together was what we called hi of t. And so that's what shows up to govern this evolution at t prime times the wave function psi I of t prime. So this integral equation is not really a solution. It has the state on the left and the state inside the integrand on the right. But the advantage is that this one can be nicely iterated order by order. And so the last step was to transform back to the lab frame. And so if I plug in this transformation again to that integral equation, I get the solution for psi of t. So we have psi of t is u naught of t minus t naught psi naught, psi of t naught, minus I over h bar integral dt prime from t naught to t. And then we had u naught of t prime minus t, excuse me, u naught of t minus t prime, h1 of t prime, psi of t prime. So again, this is an integral equation. And by iterating this thing, we get exactly this formula back. So this is u naught of t minus t naught, psi of t naught, minus I over h bar, integral from t naught to t, dt prime, u naught of t minus t prime, h1 of t prime. This one I write as the Bayer propagator plus the second order correction. So this is u naught of t prime minus t naught, psi of t naught, plus higher order corrections. So this gives me my wave function at state psi of t in terms of the initial condition psi of t0, and that's exactly equivalent to defining this propagator. So I can essentially write down exactly the same equation that I'm just erasing. Dressed propagator u of t, which came from an initial condition at t naught, is Bayer propagator t minus t naught, minus I over h bar integral dt prime from t naught to t, Bayer propagation to t from t prime, perturbation at time t prime, Bayer propagation to t prime from the initial condition at t naught, plus higher order corrections. So this is the expression to first order in perturbation theory, and that's the extent that we're going to work with today. So only two trivial things have changed about this equation from the one that I just erased a minute ago. One is that now there's a t prime, which is sitting here in the interaction Hamiltonian. Nothing really changed because this thing was already time ordered because of the ordering of the factors. So making it time dependent didn't upset anything. And the other thing was that we allowed for a more general starting point, t naught, which didn't have to be at t equals 0. So all of the results that we'll be talking about today for time-dependent perturbation theory come as a consequence of this equation. So if you have in your head a solid picture of what this dressed propagator looks like, you can quickly derive anything that you need for time-dependent perturbation theory. All right, so there are a few quantities that we will be discussing today relevant to this time dependence. So things we would like to calculate. So first we want to talk about transition amplitudes. So this is something like starting in some initial state I at time t naught, evolving it with the dressed propagator in perturbation theory and asking what is the amplitude to find yourself in state f at the end of it. This is sort of the building block for everything else. Up to some phase factors, this is what Shankar calls the coefficient d sub f, or d sub f I of t. So the second thing, which is of course related to the transition amplitude, is the transition probability. So this is the probability to find yourself in state F starting from initial condition I as a function of time. That's, of course, just this amplitude squared. And of particular interest will be the case when you're looking in the far future. So you say, as t goes to infinity, what is the probability that my time-dependent perturbation will cause the transition from some initial condition to something at the end of time? So, and then there's the long time behavior. So I would just call this PFI with no time argument. This is the limit as t goes to infinity of exactly the same quantity. And this could be given an initial condition at t equals 0, what happens at infinity, or it could be given an initial condition at t equals minus infinity, what happens at t equals infinity. The last thing that we'll want to look at happens when you have a perturbation that is driving a transition sort of constantly. It's similar to a driven differential equation. If you have a transition that is allowed and you are driving the transition at that allowed frequency, it's sort of like having a system at resonance. So at resonance, you are causing an increase in this probability as a function of time. And then it makes more sense to talk about the transition rate. So that I will call RFI. And this is the limit as time goes to infinity of that probability PFI of t per unit time. So if I have an external perturbation that is driving a transition, then I will ask, what is the transition rate to a different excited state as a function of time? Because the probability itself will be increasing. All right, so these are the quantities that we would like to calculate, and we have all the tools necessary to do it. So before we look at the extra complications that come from a time-dependent perturbation, we can answer some of these questions already for a time-independent perturbation. If I have a time-independent perturbation, I can work out the transition amplitude and I can figure out the probability and the rate to go to a different state. So let's look at that case first. Let's start with the same case that we discussed before, where I'm starting off with an initial condition at t0 equals 0, and I'm asking what is the amplitude or the probability to find myself in state F at a later time. So here I'm writing state F, u of t, I. I won't write the 0. So this is the bare propagator, u naught of t, minus I over h bar integral dt prime from 0 to t, bare propagation to t from t prime. In this case, a time-independent perturbation h1 times bare propagation from 0 to t prime. And I forgot to sandwich this thing between states. So final, initial, plus dot, dot, dot. So if these initial and final states are eigenstates of the bare Hamiltonian, then this quantity, for instance, is just final e to the minus I over h bar, bare Hamiltonian h naught, t, I. So this quantity is an eigenstate of the bare Hamiltonian, so this is just, let's say, e to the minus I over h bar, energy of the final state times time, times the overlap of final with initial, and this is just a Kronecker delta. So this is e to the minus I over h bar, e final times time, Kronecker delta, final state equals initial state. Something similar happens for this term. When I have this thing sandwiched between eigenstates, U naught t minus t prime, H1 U naught t prime, initial state. This thing acts on the eigenstate to the left, and so I get just that phase the same as this, e to the minus I over h bar e final t minus t prime. And the state f comes through. On the right, U naught acts on this eigenstate and gives me a phase factor, and the state I comes through. So I have the perturbation H1 sandwiched between the initial and final states times a couple of phases, e to the minus I over h bar, e initial times t prime. So I'm going to clean up the expression. I notice that I have the same phase factor here, e final times time, and here, e final times time. The t prime dependence involves the difference between initial and final energies. So for this time-independent case, if I pull out that common phase factor, e to the minus I over h bar, e final times time, what I have left is the Kronecker delta, delta fi, minus I over h bar, integral dt prime from 0 to t. I have the time-independent matrix element, f h1i, times the phase factor e to the plus I over h bar, e final minus the initial times t prime. In principle, I have higher order corrections that can be sitting inside this bracket. But no matter which higher order correction I have, I'm always going to have this phase factor e to the minus I over h bar, e final times time. Because this dressed propagator always ends with the bare propagation to that state t final. Okay, so I have some overall complex phase out front, but the really important part is this one, the factor in brackets. This is the part that Shankar calls D sub F. I can go further than this because in time-independent perturbation theory, that matrix element is time-independent. So if I pull that phase factor out front, pull that matrix element out front, I have minus I over h bar, final, Hamiltonian, initial, and then the time integral is 0 to t dt prime, e to the I over h bar, e final minus e initial times t prime. And I can do this integral. This is straightforward. So this is 1 over this factor, I over h bar, e final minus my e initial times that phase factor evaluated at the limits. So this is e to the I over h bar, e final minus e initial times t minus 1. Because here I chose my initial condition to be at t equals 0. And lo and behold, the I h bar here cancels the I h bar there. Minus sign flips the order of these factors, and I get something that looks familiar. I get e to the minus I over h bar, e final times time as an overall factor, Kronecker delta. I'm using up the minus, so this is now plus final perturbation initial over the energy that I have minus the energy that I want times some phase factor. And in principle, there are higher order corrections sitting there. So this is a formula that we derived previously. At the time, I was trying to motivate where these formulas come from for time-independent perturbation theory, that this energy denominator here is really associated with a time scale coming from this time evolution operator. So now let's take it a little bit further. All right, so this was my transition amplitude final U of t initial. Everybody with me so far? Any questions? Okay. I guess maybe let me point out these phases because this is the part that we're going to need to massage next. This describes the amplitude for transitioning from state I to state F in a time interval roughly h bar over delta E. But the time dependence is complicated. There's some flow of probability in and out. And so that interference pattern caused by that time dependence is where the complication of the transition probability comes from. So if I square it, then I get the transition probability. So P final initial as a function of time is that transition amplitude squared. When I square that thing, this overall phase factor in front goes away. It's totally irrelevant. So for our purposes, this will single out the factor in brackets. Now I have to consider what happens if I'm in the same state or I'm in a different state. Most of the time, I'm going to be talking about transitions to a different state. So let me assume that final is different from initial, so I don't have to include that Kronecker delta as well. So let's take the transition to a final state F different from I. Then that gives me just the absolute value square of this piece, the real action part. So I have absolute value squared of final Hamiltonian initial divided by E final minus E initial, E initial minus E final. And then my phases were E to the plus I over H bar, E final minus E initial times time minus 1. And then I square it. So the numerator squared is just the square of the matrix element. The denominator is E initial minus E final squared. The real important part comes from squaring this complex phase. So absolute value squared means take the factor and multiply it by its complex conjugate. So when I multiply 1 times its complex conjugate, I get 1. When I get phase times its complex conjugate, I also get 1. So those two perfect squares give me a factor of 2. From the cross terms, I'm going to get a minus sign, and I'm going to get e to the I thing plus e to the minus I thing. That is a cosine. So that is 2 times cosine of this argument. That is e final minus e initial over h bar t. So I can massage this expression a little bit, pull out a factor of 2, and I get 1 minus cosine. I use the double angle formulas, and I can replace cosine in terms of sine squared. So this is equivalent to 4 sine squared of E final minus E initial over 2 H bar times T. So I use the double angle formula to expand cosine and convert it to sine squared of 1/2 the argument. So I think this shows the transient nature of the quantum probability flow very clearly. So what we find is that the probability to land in final state F, starting in initial state I as a function of time, is an overall magnitude, final state, perturbation, initial state squared, divided by energy denominator squared, times 4 sine squared E final minus E initial over 2 H bar times time. So I would say that this describes the transient flow of probability. That sine squared function is doing this.
peaks at 1, it starts at 0. On average, it's a half.
So probability flows into state F, probability flows back out from state F, but on average, not really anything is happening. On average, this thing is just sitting at a constant value. So this perturbation is not actively driving a rate. There's some constant probability, but you're not increasing the probability to be in any particular state as a function of time. As long as this thing is oscillating. So that's critical. As long as E final minus E initial is not equal to 0, then you have this oscillation. I would associate this with that transient flow of probability or virtual quantum fluctuations. It's no accident that this is related to energy conservation. In quantum mechanics, the uncertainty principle allows you to violate energy conservation due to quantum fluctuations over a short period of time. So your energy that starts out E initial doesn't have to stay E initial. It can temporarily fluctuate out, but it's always got to fluctuate back. So that's what's driving this virtual fluctuation into state F and then back out. But overall, nothing is happening because a real transition would be forbidden by energy conservation. The only exception to this is if that phase is equal to 0. If E final minus E initial is equal to 0, this would be the case of degenerate states. If I have two states at the same energy, then that means that at any time, this difference is 0. Now, of course, this denominator is also 0, so I've got to carefully take the limit. In the limit where this thing goes to 0, then my sine is approximated by its argument. Sine theta is approximately theta. So I get EF minus EI squared. That cancels the singular part down here, and I get T squared. So if this is true, my P final initial of time is proportional to T squared. So this is actually not just fluctuating in and out. This is actually growing as a function of time. If it's growing as a function of time, then I can ask, what is the rate of transition? The transition rate. So that transition rate, our final initial, is the limit as t goes to infinity, that probability P final initial of time divided by time. So if I take this expression and I divide by time and I take the limit t going to infinity, I get final Hamiltonian initial squared, and then let me write this as times limit as t goes to infinity. I've got 1 over that energy denominator down here, E final minus E initial squared, 1 over time, sine squared, E final minus E initial over 2h bar times time. So if you stare at this function for a second, you realize, okay, if t is not, if the argument is not 0, then I have this oscillating situation. Then this thing stays constant on average, and when t goes to infinity, it goes to 0. On the other hand, if the energy difference is 0, then this thing grows like t squared. So it goes to infinity. So this is an object that is 0 if the argument is 0. It is 0 if the argument is non-zero. It is infinity if the argument is 0. And if you check it, it has a finite integral. That's your warning bell that this thing is actually a delta sequence. This is going to become a delta function in the limit when t goes to infinity. So let me, for illustration purposes, show you what that plot looks like. You guys seeing my screen?
Yes.
Okay. So here's that function, sine squared omega t divided by omega squared t. This blue curve is for t equals 1. The yellow curve is for t equals 10. It has some funny oscillations, but as time gets larger and larger, indeed, it starts to go to infinity and it concentrates the weight around 0. If you ask Mathematica, it will tell you that the integral of this thing is pi. So in the limit when t goes to infinity, this strange function is pi times the delta function of its argument. So that's what we're going to use. Okay. So to make this prefactor equal to that argument, there's this extra factor of 2h bar. So I'm going to multiply and divide by 2h bar squared. Except I lost my factor of 4. I already had the 4 to begin with. Maybe let me put that up front. So this thing in the limit when t goes to infinity becomes pi times a delta function of what's inside here. Delta function e final minus e initial divided by 2h bar. And if I massage the argument of the delta function, then this is 2 pi h bar, energy conserving delta function, e final minus e initial. And now I clean up all of my factors. The 4 cancels the 4. I've got 1 over h bar squared here and an extra factor of h bar there. At the end of the day, what I obtain is something with clear physical meaning. So that transition rate to final state F from initial state I works out to be, I have 2 pi over h bar. That's this 2 pi and an overall 1 over h bar from this matrix element squared, final Hamiltonian initial squared times energy conserving delta function, E final minus E initial. So this transition rate is our first appearance of what's called Fermi's golden rule. This is the time-independent case. When the frequency of the time dependence is equal to 0. So in this case, if we had a time-independent perturbation, the energy is not conserved. When time goes to infinity, final energy must equal initial energy. That energy-conserving delta function enforces this. But I can still have transitions between degenerate states. So if I start off in one perfectly good eigenstate, which is degenerate with some friends, I have a little perturbation. I'm not allowed to jump to any other excited states. But if I cause a transition from one degenerate state to another degenerate eigenstate, then the probability flows out of initial state into final state, and it does not have to flow back. That's what this is telling us. So this overall factor of 2 pi over h bar, you can kind of think of being associated with the delta function. Delta functions often come with factors of 2 pi from Fourier transforms. This is my energy conserving delta function. And then this is my transition matrix element. So the key features that went into this were A, recognizing that weird delta sequence, but B, separating out the temporary or transient virtual fluctuations of quantum mechanics from the real allowed transitions which are governed by energy conservation. The same essential story will be true when we have a periodic time-dependent perturbation. We will consider the case Hamiltonian as a function of time is a time-independent bare Hamiltonian, and then the time-dependent piece comes with e to the minus I omega t. The story will be almost exactly the same as the time-independent case, but the difference is that now this oscillating perturbation is going to be driving energy into the system. You can think of this like an oscillating force. And so if you are oscillating the system at resonance, you can be driving energy in or driving energy out. And that will lead to a shift in this energy conserving delta function. So the picture I would associate with this in perturbation theory is when I have something like this, I have an insertion of the perturbation, H1, but this is now injecting a frequency into it. And that corresponds to injecting an energy, H bar omega. So I will start off with some energy EI in the initial state, and I will end up with energy E final equals E initial plus H bar omega. So we'll work this out. It's almost identical to the case we just did before, but now we are driving energy into the system with the periodic perturbation. Everybody with me so far? Any questions?
Is this, I mean, I don't know, at the very basic, it looks kind of like absorption and emission.
Yes. Absolutely. So this is the foundation of scattering theory. So it is no accident that the natural way to think about this problem is with the absorption of a particle, essentially, the absorption of a wave with definite energy. So I draw it this way on purpose to make you think of it like absorbing a photon. And when we do time-dependent electric and magnetic fields, that's exactly what it's going to be. So we will build scattering theory out of essentially this ingredient. Any other questions? Okay, so let's repeat the process now where I have this time-dependent phase. So now my transition amplitude to state F, let me make sure I'm setting this up the same way as in Wallace. Yeah, so let me do the same thing where I'm taking my initial condition to be t equals 0. We won't always do that. So same setup, final state, time evolution operator, U of t, initial state is final state, Baire propagator. Initial state minus I over h bar, integral dt prime from 0 to t. Final state, Baire propagator to t from t prime times perturbation h1, which is now h1 times e to the minus I omega t, times Baire propagation u naught to t prime from 0, initial state. So in the same way, I evaluate the Baire propagator on the eigenspace. So I get e to the minus I over h bar, e final times time, delta final state, initial state, minus I over h bar, integral dt prime from 0 to t. Here now I have when this Baire propagator acts on the final state, I get the same base factor as before, e to the minus I over h bar, e final, t minus t prime. Now I get an extra factor with time dependence, e to the minus I omega t, and the matrix element that's left, aside from that factor, is still time independent. Final Hamiltonian initial, and then when this Baire propagator acts on the initial state, I get e to the minus I over h bar, e initial times t prime, plus higher orders. So in the same way as before, I pull out the common phase factor for the endpoint, and I'm left with delta final initial minus I over h bar. Again, the matrix element which is doing the transitioning is time independent. And now my t prime integral contains this extra factor of omega. Integral from 0 to t dt prime, e to the plus I over h bar, e final minus e initial minus h bar omega, t prime, plus higher orders. So you see exactly this picture that when you have an oscillating perturbation, it is effectively adding energy h bar omega. The rest of the calculation works exactly the same way.
So my probability to land in final state F from initial state I, where I'm assuming final is different from initial,
as a function of time is exactly the same thing.
I get 1 over h bar squared, final perturbation, initial state squared,
And then I have the absolute value
squared of this integral from 0 to t dt prime, e to the I over h bar, e final minus e initial minus h bar omega times t prime. Everything else goes through exactly as before. This is absolute value squared, 1 over I h bar, e final minus e initial minus h bar omega, times the phase factor, e to the I over h bar, e final minus e initial minus h bar omega times time minus 1. Everything squared. So this again works out to cancel the h bars. Yes, this is 1 over h bar squared. This is 1 over h bar squared. So I have final Hamiltonian initial squared e final minus e initial minus h bar omega squared. And then this again becomes 2 minus 2 cosine e final minus e initial minus h bar omega over h bar times time. And this is again final Hamiltonian initial squared over e final minus e initial minus h bar omega squared times 4 sine squared e final minus e initial minus h bar omega over 2 h bar from the double angle formula times time.
So again, we see that quantum mechanics allows virtual transitions to other states temporarily, but on average, nothing happens, except when you are obeying energy conservation. So only drives transitions. I would call these resonant transitions. When E final is equal to E initial plus H bar omega. So in the same way as before, I can calculate the transition rate and take the limit t going to infinity, and I'm going to get a delta function. So this is final Hamiltonian initial squared times we had limit t going to infinity. We already have 4 upstairs, E final minus E initial minus H bar omega squared downstairs, sine squared, E final minus E initial minus H bar omega over 2 H bar times time. This thing is going to become a delta function as long as I've got 1 over omega squared, and t, that's important. I need to multiply and divide by h bar squared to make this thing become the delta function. And in the limit, this delta sequence approaches pi delta of this argument. E final minus E initial minus h bar omega over 2h bar, which is again 2 pi h bar energy conserving delta function. E final minus E initial minus h bar omega. And multiplying it all out, I again get the same factor, 2 pi over h bar, matrix element squared, times an energy conserving delta function, now including the energy being absorbed by the perturbation. And this is what is usually called Fermi's golden rule. The case we had before is obviously just the case when omega is equal to 0, which is the case of a time-independent perturbation. But the picture is the same. Quantum mechanics allows virtual temporary fluctuations in and out of other states, but that's transient if they violate energy conservation. But if you have a real on-shell resonant transition going from E initial to E final after absorption of H bar omega, you can probability out of the initial state into the final state at a finite calculable rate. All right, it's worth emphasizing, by the way, this calculation was at first order in perturbation theory. The picture can become more complicated. You can get more complicated matrix elements at higher orders in perturbation theory. But all right, let's work through an example. So let's take the simple case of a harmonic oscillator. Starting in its ground state 0 at an initial condition T naught, which we will take to be in the infinite past. T goes to minus infinity. And our perturbation will be a Gaussian pulse, which looks like an applied electric field. So H1 of T is minus electric charge, electric field times the position operator. So this looks like electric field coupling to a dipole moment. And the time dependence will be Gaussian, e to the minus t squared over tau squared. So tau tells me the width of the Gaussian pulse, and this is a perturbation that's centered around t equals 0. And so we want to know what is the transition amplitude and probability as a function of time as t goes to infinity. Transition amplitude and probability as t goes to infinity. So I start off with the expression for the Drest propagator. Final state. Now this is a time evolution operator to future infinity from past infinity. Here, maybe before we plug these in, let's write this for specific finite times. How about t and t naught, and then we'll take the limit at the end. So this is final u naught of t naught initial. And the Baire propagator just depends on that difference. Minus I over h bar integral dt prime from initial condition t naught to t. Final, I have Baire propagation to t from t prime. I have the perturbation h1 at time t prime. And then I have Baire propagation u naught to t prime from the initial condition at t naught. So this is similar to what we did before, but now we're including some initial time t naught that doesn't have to be 0. All right, so just like before, I'm going to sandwich these things between eigenstates of the Baire Hamiltonian. So this expression I can write e to the minus I over h bar, e final times time, delta final initial, e to the plus I over h bar, e initial times time, t naught. That's this first piece. Now, in this case, it's trivial. Final and initial are the same thing. So I could have called this E final times T minus T naught. Or I could have called it E initial times T minus T naught. But to make it match up with the other term, it's useful to pick the endpoint here to be E final at T, and the initial point here to be E initial at T naught. So let's continue evaluating this on the other board.
So what we have there on the right-hand side, the second term, we had minus I over h bar integral dt prime from t naught to t, final u naught of t minus t prime, h1 of t prime, u naught of t prime minus t naught times the initial state. So this guy, just like before, is e to the minus I over h bar, e final, t minus t prime. And then the state f comes through, h1 of t prime. Here the state I comes through, and it gives me a phase factor e to the minus I over h bar, e initial times t minus t naught.
So if I pull these things together, I can pull out that E initial times T naught at the end, just like here,
and the E final times time in the front. So this is E to the minus I over H bar, E final times time sitting in front. Minus I H bar, integral dt prime from T naught to T. I have the perturbation, H1 of T, initial, the t prime dependent stuff here is e to the plus I over h bar, e final minus e initial times t prime. And then at the end, I have e to the plus I over h bar, e initial times t naught.
So thus far, it works the same way as what we had before, except now I have to pull out another factor for t naught at the end, as well as a factor for e final at the front. Okay, we haven't yet plugged in what this time dependence is. This particular matrix element is just minus EE. The final state here is some state n of a harmonic oscillator. This is the position operator x, and my initial state was the ground state of the harmonic oscillator 0. And the time dependence is Gaussian, e to the minus t prime squared over tau squared. All right. So what we have is final states, dressed propagator to t from t naught, initial state equals, I have a factor e to the minus I over h bar, e final times time in front of everything. I have my delta final initial like always, minus I over h bar. I have a time independent matrix element, minus EE n x 0 times integral dt prime from t naught to t, e to the I over h bar, e final minus e initial times t prime times this time-dependent pulse, e to the minus t prime squared over tau squared. If I've got higher orders, they're sitting in here, and then always at the end I have e to the plus I over h bar, e initial times t naught. So we can continue to massage this a little bit. Notice the structure again. I have some time-dependent factor in front, time-dependent factor at the end. These make it look more complicated. It makes it awkward to take the limit when t goes to infinity this way, but it doesn't affect the probabilities. If I take the absolute value of this thing, that goes away and that goes away. So let's do that. Let's take the limit as t goes to plus infinity and t naught goes to minus infinity of that absolute value. So the purpose of that is just to get rid of these phase factors at the end that just sit there and oscillate forever, and you can't take a well-defined limit with t going to infinity. Getting rid of that, I just have delta final initial minus I over h bar minus EE nx0 times now integral from minus infinity to plus infinity dt prime
e to the I over h bar, e final minus e initial times time, times the pulse, e to the minus t prime squared over tau squared. All right, everybody with me so far? We were keeping the t and the t naught arbitrary to see the phase factors that come out of it. And then now that we've separately gotten rid of them and we see that the action is happening in these brackets, now I'm taking the limit when t goes to minus and plus infinity so that this becomes something simple. All right, we haven't yet plugged in the structure of the harmonic oscillator. I've been a little bit mixing my notation. The initial state was 0. The final state is some excited state n of the harmonic oscillator. So this initial state is E0. This is some En. Now I know how to calculate this matrix element of X in the harmonic oscillator. I write it in terms of creation and annihilation operators. I get a prefactor, which is h bar over 2m omega, n a plus a dagger 0. The annihilation operator gives 0 when acting on the ground state. The only thing that I get is a dagger on it. And I get root h bar over 2m omega. And the only excited state that I can possibly transition to is n equals 1. So that actually makes my life a little bit simpler. Let me look at what this phase factor is here. En is n plus 1/2 h bar omega for the harmonic oscillator. If n is equal to 1, that's just 3/2. E0 is the ground state of the harmonic oscillator. That is 1/2 h bar omega. So when I take the difference, I just get 1 h bar omega. Okay, so to summarize, because this perturbation is proportional to the dipole moment x, only n equals 1 contributes. The amplitude is 0 for all other states. For n equals 1, I get something particularly simple. So I have let's see, the transition amplitude to state 1. So this is now time evolution to positive infinity from negative infinity from initial state 0. I haven't squared it yet. Delta final initial, so this is delta, okay. So this was delta n0. So I can either stay in state 0, which is this term, or I can transition to state 1, which is this term. So if I'm talking now about only going from 0 to 1, I'm not including the delta function anymore. Right. So then I have minus I over h bar. Overall in front, I have minus EE square root h bar over 2m omega. And then that time-dependent integral that's left, integral dt prime from minus infinity to plus infinity, is the pulse, e to the minus t prime squared over tau squared, and I get e to the I omega t. So prefactors are sitting out in front, but what is this thing? This has physical meaning. No. Well, I don't know. No, it's not a gamma function.
It's a pi. It's a square root of pi with something.
Yeah, there's going to be square roots and things. This is a Fourier transform. I have e to the I omega t. I think the gamma function is going to have powers or something like this. This is a Gaussian. The Fourier transform of a Gaussian is also a Gaussian, so it is not a gamma function. Yes, exactly. So how do you evaluate it? You complete the square. This is integral minus infinity to infinity, dt prime, and I write this as e to the minus 1 over tau squared. In the numerator, I have tau prime squared
minus I omega t prime tau squared. That is 2/3 of a complete square. If I complete the square, then this is integral minus infinity to plus infinity e to the minus 1 over tau squared t prime minus 1/2 I omega tau squared times the missing piece, which is plus 1 over tau squared minus 1/2 I omega tau squared.
This is a Gaussian integral.
So this one gives me square root of pi times tau times this prefactor.
So we'll talk about this more in a second. It is no accident that the Fourier transform arises from this time-dependent pulse.
So we have integral minus infinity to plus infinity, dt prime e to the minus t prime squared over tau squared e to the I omega t prime.
And what this gave us was
Tau square root pi e to the minus 1/4 omega squared tau squared.
So this object was Gaussian in T prime. This one is Gaussian in omega. Fourier transform of a Gaussian is a Gaussian. So let me comment, this Fourier transform is another way of saying the pulse itself
Can be written as a superposition of frequencies. So the original pulse, e to the minus t prime squared over tau squared, if I use the inverse Fourier transform, is an integral over various frequencies omega, minus infinity to plus infinity. This coefficient times a pure oscillating phase, e to the minus I omega prime t prime.
So if I wanted to, I could have taken this original pulse and by Fourier transform, I could have written it in a form like this that I could plug into Fermi's golden rule, something that looks like a pure phase. So this time-dependent Gaussian pulse is really a superposition of a bunch of plane waves, and that's why the Fourier transform shows up. Okay, so finishing the calculation of the transition amplitude. This is one time evolution to infinity from minus infinity 0. So overall in front, I have E H bar, I have E square root H bar over 2m omega. I have from the Fourier transform a square root of pi times tau. And then I have e to the minus 1/4 omega squared tau squared. Make sure I didn't drop any factors. There was a 1 over h bar. Yes, this 1 over h bar. Okay, very good. So this is my transition amplitude aside from those ill-defined phases at the very front and the very back. Squaring this thing gives me the transition probability. This is the transition probability in the limit when time goes to infinity. So that's P final initial as absolute value squared. In this case, the final is 1, the initial was 0. And then squaring the answer is trivial. E squared over h bar squared, h bar over 2m omega. I have pi tau squared e to the minus 1/2 omega squared tau squared. So if you want, you can simplify it a little bit, but this is it.
So importantly, we got a finite transition probability. We did not get something which was diverging at resonance to infinity and we needed to calculate a transition rate. We just got finite number. So what's happening in this example? So what we had was that time-dependent pulse, h1 of t, was minus EEX. This is what determined which transitions were possible. And it had a time-dependent profile, e to the minus t squared over tau squared. So that perturbation, h1 as a function of time, the Gaussian pulse centered around 0 with a characteristic width tau. So this is a range of times. And what we saw is that that time-dependent profile can be converted into a superposition of frequencies by Fourier transform. Integral d omega prime over 2 pi, the same operator minus EEX. And then this became the Fourier coefficients, tau square root pi e to the minus 1/4 omega prime squared tau squared times a pure phase, e to the minus I omega prime t. So that's telling me that this time-dependent pulse is equivalent by Fourier transform to a superposition of frequencies. So let me call this h1 of omega, the frequency distribution, as a function of omega. And maybe let's call this omega prime to differentiate it from the omega in the harmonic oscillator. The Fourier transform of the Gaussian is a Gaussian. So my frequency spectrum looks like this, and it has a different width. The characteristic width here is 2 over tau. So this is my frequency spectrum. So that means in my harmonic oscillator, I started off at the ground state. So I started off in the state 0 with E0 is 1/2 h bar omega. I'm looking for a transition to the state 1, which is allowed by this matrix element. This has energy E1, which is 3/2 h bar omega. The energy that it takes to drive a transition from one to the other is exactly 1 h bar omega. And when I Fourier analyze the pulse, it has a whole bunch of frequencies. One of them is guaranteed to work. So what this expression is doing is it's finding the specific frequency, omega, which is the one necessary to drive that transition, and it singles out that one Fourier mode out of this distribution. This one, omega prime equals omega, was exactly the one mode that contributed. So another way to say this is that time-dependent pulse is a superposition of frequencies, and we're picking out exactly the right one which has the correct energy to drive this transition. So I would say the fundamental understanding of time-dependent perturbation theory is coming from that frequency analysis. It's coming from Fermi's golden rule. And anytime you have a time-dependent pulse like this, it's always going to work out this way. You're always going to Fourier decompose it. And you're always going to select out the exact frequencies that are necessary to drive the allowed transition from one state to another. If I could drive the transition from 0 to another excited state, like 2, then I would pick out this frequency for that transition and another frequency for the second transition. But I get something finite because I've essentially integrated over the delta function. If I was driving this transition at exactly that resonant frequency, I would get an infinity, and I would have to calculate the transition rate as a function of time. But since I've got a whole spectrum of it, I integrate over the delta function, and I get something finite just from picking up the one particular frequency. Okay, any questions on this? So if you wanted to drive the transition the other way from 1 to 0, you would need the negative energy component. So instead of the positive omega piece, you would pick up the negative omega piece. And this distribution, sure enough, has exactly that too. So if I started with the initial condition 1 and asked about the transition to 0, then I could get it from the x operator. And I would pick out the omega prime equals negative omega component. Does that make sense? Yeah. So because this pulse is a superposition of all infinity frequencies, you will always be able to find the frequency you need to drive the desired transition.
Can you read out what the width of that graph? I see something over tau, but I don't know what the
Sorry, this width is 2 divided by tau. So because of this 1/4, so this is e to the minus omega prime squared, that's Gaussian, and the width is 2 divided by tau. So if this one is narrow in time, this one is wide in frequency, and vice versa.
Okay, thank you.
So that is 2 divided by tau. Okay, we're out of time. I don't want to start anything new at this point. The main point is that you should think about the natural picture of time-dependent perturbation theory as this propagation and absorbing frequency modes. Any kind of time dependence will always have this picture, even if it means you've got to take some time-dependent function and Fourier decompose it, and then look at the superposition of all of the possible frequencies that can be absorbed by the system. Okay, next time we will talk about limits of this. So there's very simple cases, either when the perturbation is very fast or when the perturbation is very slow. This is called the adiabatic approximation or the sudden perturbation limit. And we will also revisit the case of paramagnetic resonance, the time-dependent problem you guys did for homework before, and we will reinterpret that same problem from time-dependent perturbation theory. All right, that's it for me for today. Any other questions before we adjourn?
Thank you.
Thanks very much. Don't forget the regrade by Friday night.